Hello and welcome. Today we're going to jump into one of the most incredible stories in all of science. It's the story of how our idea of the atom went from being this tiny little solar system to the absolutely wild, fuzzy quantum picture we have today.
So, where do we even begin? Well, like any good detective story, this one starts with a deep mystery. For years, scientists were completely stumped by one question. Why does every single element have its own unique signature, a kind of fingerprint made entirely of light? So, here's how we're going to crack this case. We'll start with that initial puzzle, the atom's fingerprint. Then, we'll look at Bohr's brilliant first crack at solving it, and where that theory fell short. After that, things get really weird with a full-blown quantum revolution, which finally helps us decode the electron's true identity. And we'll wrap it all up by thinking about what this means for, well, reality itself.
All right, let's dive right into that central puzzle. Imagine you take an element, any element, and you heat it up until it glows. Now, the physics of the day, what we now call classical physics, predicted you should see a full, continuous rainbow of light. But that is not what happened, not even close. Instead, what they saw was a series of sharp, distinct lines of color. This line spectrum was the first major clue that something really, really strange was going on inside the atom.
And this visual just nails the problem, doesn't it? On one hand, you've got what everyone expected, a smooth ramp of energy where any value is possible. But on the other hand, you have what we actually found, a staircase, where only specific, separate energy steps were allowed. These were two totally different pictures of the universe, and they couldn't both be right.
So who's going to solve this? Enter the Danish physicist Niels Bohr in 1913. He steps onto the scene and makes this incredibly bold first move to explain those mysterious atomic fingerprints. He took the existing model of the atom, the one with a nucleus in the middle and electrons zipping around it, and decided to fix it.
And his idea was, well, it was completely revolutionary for the time. He said that energy inside an atom is quantized. What does that mean? It means it's not a smooth, continuous flow. Nope. It comes in these tiny, distinct packets called quanta. It's just like that staircase again. An electron can be on this energy level or the next one up, but it absolutely cannot float in between.
So how did this whole quanta idea explain the fingerprint? It's actually a pretty elegant four-step dance. First, an electron absorbs a precise packet of energy, and poof, it jumps up to a higher level. But it's in excited state. It can't hang out there forever, so it falls back down. And as it falls, it spits out that exact same packet of energy, but this time as a particle of light, a photon. And the specific color of that light depends on how big the drop was. That's it. Each line in that fingerprint is just a different electron jump.
And you know what? It worked. It was a massive success. For hydrogen, the simplest atom there is, Bohr's model predicted its fingerprint perfectly. With incredible accuracy. It really seemed like the case was closed, mystery solved. But as you might have guessed, the plot was just about to thicken.
Because that's the thing with science, isn't it? A great answer always leads to even bigger, tougher questions. And it wasn't long before people started to notice some serious cracks in Bohr's beautiful model.
Yeah, the issues started piling up pretty fast. It worked for hydrogen, great, but try it on any other atom with more electrons? The model just fell apart. It had nothing to say about how atoms bond together to make molecules, and the biggest issue, really, was that it was still thinking of the electron as this tiny little marble running on a flat 2D racetrack. That entire picture was about to get blown to bits.
This is where things go from just being a little weird to a full-on quantum revolution. A whole new crew of physicists comes along, and their ideas are so strange they sound like something out of science fiction. But these bizarre ideas were exactly what was needed to get to the real truth.
First up, Louis de Broglie comes out with this absolute jaw-dropper. He proposes that the electron isn't just a tiny ball. It also behaves like a wave. Think about that for a second. A particle and a wave at the exact same time. This idea of wave-particle duality didn't just change the rules. It basically threw the whole rulebook out the window.
And if that wasn't mind-bending enough, along comes Werner Heisenberg to completely demolish the idea of a neat, predictable orbit. His famous uncertainty principle says that it is literally impossible to know both an electron's precise location and its precise momentum at the same instant. It's not that our tools aren't good enough. It's a fundamental rule of the universe. And if you can't know where it is and where it's going, how on earth can you draw a path for it?
So, with these new, strange rules in play, Erwin Schrödinger steps in and creates a masterpiece of mathematics. He develops an equation, but this equation was different. It didn't even try to tell us where the electron is. Instead, it gave us something much more powerful, a map of probabilities. It described a region of space and told us the chances of finding the electron at any given spot.
And that's how we finally get from the old idea of an orbit to the modern concept of an orbital. So forget the flat racetrack. An orbital is a three-dimensional, fuzzy cloud of probability. The denser parts of that cloud are simply where you have the highest chance of finding the electron at any given moment.
Okay, so if we've got these fuzzy clouds, how do we describe them? And how do we keep track of the electrons inside? Well, scientists came up with this really ingenious system, a set of 4 quantum numbers. The best way to think of it is like unique, super-specific postal address for every single electron in an atom. No 2 electrons in the same atom can have the exact same address.
Let's break down that address. First, you've got the principal number, n. That's like the state and city. It tells you the main energy level and the overall size of the orbital. Then, the angular momentum number, L. That's the street name. It defines the orbital's actual shape. Next is the magnetic number, m sub L, which is the house number. It pinpoints the orbital's orientation in 3D space. And finally, the spin number, m sub S, is like the person living at the address. It's a unique property of the electron itself, either spin up or spin down.
And these numbers are what give us these really cool, distinct orbital shapes. For instance, an s orbital is just a simple sphere, but the p orbitals are more complex. They look like 2 balloons tied together, like a dumbbell, and they can be oriented in 3 different ways, one along the x-axis, one along the y, and one along the z.
And all of this complexity leads to a beautifully simple and fundamental rule, represented by this number. Any single orbital, no matter its shape or size, can hold a maximum of 2 electrons. That's it. And for that to happen, their spins have to point in opposite directions, one up, one down.
So, just look how far we've come. We started our journey with a simple, predictable little solar system model, and we've ended up in a strange, probabilistic world governed by waves of chance. But here's the thing. This quantum model is incredibly powerful. It explains everything from the brilliant colors of fireworks to the very chemistry that makes life itself possible.
And this leaves us with a final, profound question to chew on. If the very foundation of matter, the stuff that makes up you, me, and everything we see, isn't solid little objects, but actually waves of probability, what does that imply about the solid, predictable world we experience every day? It's a real mind-bender, and it just goes to show you that science is a journey of discovery that truly never ends.